I hope everyone is with us. Right, so we want to approximate the complicated function we are trying to minimize at the current iterate, at the current approximation xk by some model. That's a simpler model. So instead of minimizing this complicated function f, we minimize this simple model. So of course we have to generate many models and sequentially. So what is this? What this simple model could be? Well, linear Taylor approximation or linear or quadratic Taylor approximation of my function around this based on the xk. These are the simplest ideas, and then I would minimize this model. That would give me a change that I would append to the current xk to get my next guess of the solution xk plus 1. And then when the gradient at the current at the iterate point xk or xk plus 1 gets small, I stop. So again, if just to fix ideas here, if I could have this linear model, then with the gradient here and the function, so I need this problem information from my algorithm, then when I minimize this model, I would get what you know as gradient descent methods, essentially the class of gradient descent methods. If I have a quadratic model so that I have gradient information and second derivative information about my point at my function at the base point, then I get so-called Newton type, second order type. Okay. Now, if I just minimize these models and bend that direction to my iterate, I will not get a method that converges from an arbitrary starting guess. So I need to be a bit more careful. I need to safeguard my step that I obtain from minimizing these models. I need to safeguard it with some techniques to ensure that f decreases along my direction. So I can cut it with line search, or I can say I only trust my model in a certain region, or I can try to control the length of my step implicitly through regularization. This is what I will only talk about today, this regularization safeguarding techniques appended to these fundamental type of directions and other type of directions. This is the core really of all methods for non-convex and even convex optimization, and there is a lot of software that implements these ideas suitable even for large-scale problems. What kind of analysis do we have? Well, we can give guarantees of behavior from such algorithms. For example, traditionally, you can show that if wherever you start from, you can generate iterates such that the gradient at the iterates converges to 0. So you have this global limiting result, global in the sense of from any starting point, not that you find the global minimizer. Another type of convergence is local convergence. So if you assume you're sufficiently close to a solution, can you be attracted by the solution, and how fast can you be attracted? So this is what you learn a lot in degrees, where in math degrees you show that steepest descent, gradient descent is linearly convergent close to the solution, and Newton has this fast quadratic rate, or often called exponential rate, locally. Now there is another thing we care about, global rates of convergence. We have local rates, very well known, very classical. But what about global rates, especially when the function is non-convex? This has been far less studied. So these global rates are in addition to global convergence. So you know that the method converges, but how fast does it converge to a stationary point? So from any starting point, that's what global stands for, from any starting point at 0, anyway in the domain, how many iterations will I take to generate a small gradient? So rates of convergence. Now, in the case, this is essentially equivalent to so-called worst-case evaluation complexity or oracle complexity. How many calls to the black box that gives me function values, gradient values, maybe secondary derivatives do I need to make to get that approximate solution at the end? So this is something well studied for convex problems. There is this amazing textbook of Nemirovsky and Yudin from '83. There is the work of Nesterov, Pavasis, Sirkovsky. These are people who have done a lot of work in this area, especially for convex problems. For non-convex problems, people thought, well, that's harder. We don't know quite how to quantify this. But in the last 15, 20 years, there's been a lot more in that, and that's what this work that I will talk about fits into. Okay, so what can we then say for non-convex landscapes? So let me give you a bit more about the this global rate story, and then I will tell you where we go with that. So I need to still build a bit of background just to put some context. So though locally gradient descent and Newton are fundamentally different, globally what we showed is that they are very similar. So if Newton is started far away, then it's actually, its behavior, its rate is very similar to gradient descent. When it converges, you can show that, you can give these examples, constructed examples, where even if the function f is smooth, global Lipschitz, gradient, Hessian, and so on, you get that Newton and steepest descent essentially look the same from a rate perspective. So then the question arose, like, is there, because Newton also with lines, with transregion, with any of these classical frameworks, the worst case bound is the same as steepest descent, and it's sharp. So the question then is, can you do better than that? And it turns out that regularized Newton, a certain type of regularization, will give it better, in fact, optimal complexity. So here's a table of what kind of bounds we can have. So these are all sublinear rates of convergence for non-convex landscapes. So to get a gradient small than some epsilon 1, say, steepest descent is epsilon -2. Newton with all classical transregion lines, which is epsilon -2, as I said, and these bounds are sharp. Then cubic regularization is epsilon -3/2. So this is better for epsilon between 0 and 1, the small epsilon, okay, than these bounds. And then there are versions of transregional line search that also have the same complexity of arc that were built based on this cubic regularization framework. And then we can also give guarantees for second order, but I don't need to talk too much about those. This big O includes Lipschitz constants of the gradient and the Hessian. And what is interesting is that this bound here of epsilon to -3/2 is actually sharp and optimal for second order methods. So within the class of when you have a function f that has Lipschitz continuous Hessian and even gradient if you want. So you have Lipschitz continuity of the Hessian. This is the best you can obtain for second order methods. So Newton type methods can be at best this bound is not only sharp, but it's the best it can be for second order smoothness with second order oracle problem information. Okay, so where is this improved bound coming from? Just to give you an idea, to go back to my models, the local models. So this was very nicely described in a paper, in a pioneering paper of Nesterov and Poyak, but then it turned out it was discovered independently by other people as well. So in the presence of Lipschitz continuity of the Hessian, no convexity, making no convexity assumptions anywhere, you can have this fundamental property in any analysis textbooks that the function f can be upper bounded by this model. Okay, so this model here in the first part has just the second order Taylor model that I said is my local model for Newton type methods. And then I do this regularization. So this is you add this regularization term, which is in a 2 norm and has power 3 here. Okay? And this is the Lipschitz constant of my Hessian. So you can prove that for any S, this model sits above the function. So when I minimize this model, with respect to S, then I make my function f go down locally. Okay, so this is very nice, right? So I can use this in my algorithm. So this is very well known, but the idea to use this as a local model of my function is new. This regularization with the third power of the step is new. So this is the so-called cubic model. So Nesterov said, okay, so just minimize this with respect to S, even if this model may be non-convex when f is non-convex. This is possible, and this can be done even tractably. So do this, and make that your next guess of the solution. You even minimize this model globally, you can do that. And what he showed indeed is that you have this upper bound on the number of evaluations you get, so you get the rate to get the gradient below epsilon. The downside here was in this paper for 06 was that you use the Lipschitz constant of a function in your algorithm. This is very hard because in practice you may not have this, the function may not have this Lipschitz constant. So can we make this a practical, a computationally efficient framework, just like lines, just like truss region for nonconvex optimization? Can you just give a code that doesn't have this? So we are going to drop this Lipschitz constant here and modify it by a regularization weight sigma k. So then, of course, we have to pay something for this. So we have to evaluate the function f and decide what should we do with this regularization weight, this parameter that we now have to adjust with the run of the algorithm, right? This will be some kind of approximation of my Lipschitz constant that I will adjust. Okay, so indeed, so we will adjust this sigma in the run of the algorithm to make progress, to try to kind of adaptively guess your Lipschitz constant without explicitly estimating it. The other thing we are going to drop is this requirement to minimize the model, the local model globally. Though it's possible, I will show you later why and explain, it's very important to just require some approximate conditions, so just local minimization. So just the model decreases from the current base point, and then we want just the small, just think of this condition as the gradient of my model has to be small. So when I minimize this model, I have to minimize this model to get my next step, SK. I don't do it globally to find a global minimizer of this model. I just find an approximate local minimizer. That's the main idea. So, and then, okay, you don't need to know all this. Just know that then I have to decide how I make progress. So I'm going to evaluate if my function decreases, and with respect to the model decrease, the model always decreases because I minimize it, but does the function also decrease? If that's the case, then I take my step, otherwise I stay at the same point and I adjust sigma. So I increase the weight. So the thing to remember is that sigma here increasing makes my step shorter, gives me more chance of decreasing my function. Okay. So the good thing is that this very practical framework that's now in a lot of software actually has the same global rate, provable global rate as Nesterov and Boyok's more theoretical framework. Okay, so indeed we can recover this epsilon to -3/2 for this practical method. We can make it scalable. We now only need these local subproblem solutions. Okay, so finally, again, the topic of my talk here. So what I want to tell you today, of course, is I want to reach higher degree polynomials. I want to talk about tensor methods. So, can I go beyond Newton's method? I told you that we seem kind of stuck at Newton in practice, of course, and also in theory with this epsilon to -3/2. If I have more problem information, if I have more smoothness of my function, can I get better optimization? That was the question. Okay, so I'm going to assume I have third derivatives of my function, and maybe even higher derivatives. Is there a framework that will be able to, in optimization algorithms, that will be able to take these derivatives in and even give me better global rates of convergence? And then I want to say, okay, but are these better methods in practice? I want to address that question. And then, of course, I have higher degree polynomials to solve. How do I solve them efficiently? And here I'm going to talk about connections to polynomial optimization, and then more about how could we make these methods more widely used. Okay, so I described you cubic regularization for a reason. So I'm going to take that framework. Okay, so here's my cubic model, and with my sigma, and that. So what is it? It's second order Taylor expansion plus this regularization to power 3, which is the order of this plus 1, the degree, the order plus 1. Okay. Then I say, oh, I want a local minimizer of this model, and then I have some powers here that I could adjust. I have to adjust here because this measure of progress refers to the order here, so I would change that, and then the rest of the framework stays the same. If I make progress in decreasing my function, then I don't need to do anything to sigma. If I fail to decrease f, then I have to increase sigma here. So this part stays the same as for second order cubic regularization. Okay, and in fact, most things stay the same, except that instead of second order, I'm going to put a pth order Taylor approximation here and a p plus 1 power there, and adjust those other powers accordingly. So here's my ARP. It goes to a paper of origin, and a few other Brazilians and Philipton. So put pth order Taylor approximation of order p greater or equal to 2, 1. Of course, we care from 3 above, and then p plus 1 here, still the 2 norm, only require local minimization. So that's good, because now this is quite difficult. So I'm just happy to just get an approximate stationary point here. And then I'm going to measure progress with respect to this, and then the rest stays the same. Okay? So it seems a very natural transition from second order to pth order if you look at it in the right way. Of course, this took many years to get to this simplicity, but it's possible. This model, the reason you need this p plus 1 here, and what it helps with, is that this is now bounded below. A polynomial that's always bounded below always has a well-defined global minimizer for any positive sigma here. Okay. So what can we say about the global rate? Well, we can prove a global rate bound, and I will show you in this table what it is. So for p equals 2, this method is exactly cubic regularization, a version of cubic regularization that I described. So it has epsilon minus 3 halves. For p equals 3, so for AR3, we get minus 4 over 3, and p, which is better than 3 over 2. And so the bound keeps improving. Okay, it's still sublinear, but the bound keeps improving. And also for second order criticality, it keeps improving. So, okay, so these are just bounds, but are they sharp? Yes. Are they optimal? Yes. So, in what sense are they optimal? So, we only know this for first order criticality. Let me take this bound for illustration. So, within the class of functions f of objectives that I'm trying to minimize that have Lipschitz pth order derivative. So the last derivative of my function that I'm using has to be Lipschitz continuous. Then, of course, all these functions are assumed to be bounded below. Then this bound applies. So I'm using the smoothness of f. I'm using the oracle to third order, and then that's the corresponding bound. And I cannot do better than this with this kind of function smoothness and problem problem oracle. Okay, right. So I don't want to go into the proof, but I want to tell you that, of course, the key idea is this overestimation idea that I already mentioned. That the same way as for second order Taylor plus cubic stays above the function. Here you can expand to pth order with p plus 1 here. This model, this is my now my local model. Yeah. Sits above my function. So when I minimize this model, when I decrease this model, I force decrease my function, provided my regularization is large enough. Okay. Okay. So a lot of these ideas are in our research monograph, where we also address issues like, if you have this third order problem information, can you assert not just first order criticality, second order criticality of your solution, but also pth order criticality. So we also have constraints and bounds for constraint problems, and a lot more in this book. Okay, so now I want to talk about further questions from this. So here's a simple question. So, before I go on to that, let me tell you a little bit what has been happening in the convex. Okay, so I only spoke about the non-convex case. Now, if my function f is convex now, Nesterov himself has gotten into this topic, so after us, essentially. And if f is convex, here's what happens to these local models. If sigma is above the Lipschitz constant of my pth derivative, which anyway I assume it is, okay, then, rather surprisingly, I would say, this local model, the one I've used before as well, in R, this local model is now a convex function. So though this is a polynomial, right? It's a polynomial of high degree. If the function is convex and this weight is large enough, this model is convex. So that means that now we can, in the convex world, this, when f is convex, this is easy to minimize. And so also you can give better complexity bounds. So he showed that, so the methods are very similar. You know, in his framework, essentially you just give sigma a multiple of the Lipschitz constant. So you just assume sigma is large enough, then this is convex. And then with that model, with this convex model, you get not epsilon to minus 4/3, but epsilon to minus 1/3. So much better, still sublinear, but much better rate in the convex world. And okay, you can say more, you can say something about the function degree, not just about the gradient. This, in fact, the bound here can be even better, can be epsilon to minus 1/p+1 with acceleration. So you can also accelerate these methods and so on. So this work of Nesterov was followed up by many, many papers trying to show what is sharp, what is not sharp, and so on. Okay, so in the convex world, we get better bounds, and you have this very nice property of convexity. But what Nesterov does need is that f is convex globally to get this. Okay, what about locally? We saw that Newton has better rate density by descent locally, is quadratic. Now, locally for all these methods, non-convex, convex, you have piece order rate of convergence. Okay, so third order, much, much faster rates. Okay, and these plots just illustrate whether sigma is close to 0 or sigma is large. We show that these align, the behavior of the methods align very well with having third order rates compared to p equals 2 with Newton, which is second order, the quadratic rates. Okay, so these are, of course, these high rates, you won't see it numerically unless maybe you have extended precision or something like that, but this is provable. Okay, so these are natural, these methods that use these third order tensor derivatives and higher can be seen as a natural extension of second order. If you try to do your line search, it's essentially impossible with this method. If you try to do trust region, you don't get these good rates. So regularization really helps you get very good rates, very nice frameworks. Okay, so if I just use third order tensor information numerically, is this going to be better? So assume I have this problem information first, second, and third. Okay, so here are some examples. These are constructive examples, but nonetheless, here's some situations. So here's like a mountain, okay, and you're doing slalom on this mountain. This landscape here has gradient small, Hessian small, but third order information large. That's the way to think about it. So both first and second order take the long way down the mountain. Okay, they have to go slowly. But third order are these red dots that jump across these landscape. Okay, this is so in iterations with computationally provable this example, you can get very few iterations. Also in time, in these examples, you can gain. So if you gain sufficiently in iterations, then your problem information, your calculation of problem information to third order also pays off. But you have to gain quite a bit for that. Here's another example. It's like a hairpin pass in the mountain. Again, similar. First, second order here. First order, first order, second order. They have to go the long way, while third order is able to jump. So, okay, but this is just to illustrate the point of when these methods are good. What if I take, as we do in optimization, a test collection of problems, and I try to see how first and second and third order methods compare? So, fortunately, our Brazilian colleagues, Ernesto Bertrand and his team, coded up third derivatives to a well-known test collection in optimization, this MGH test collection, 35 problems. And we then went on to practical code development. And So what is an efficient way to increase the regularization parameter in these methods, how to choose your initial guess, how to make these methods efficient practically, which you always do. You do it cubic, you do it everything else. So we have this third AR3 plus, AR2 plus, so cubic plus, third order plus, that are efficient implementations where we thought carefully how to get an efficient approach here. And these are performance profiles. You may be very familiar with these. These are cumulative distribution functions of some metric. So here is we measure function evaluation, derivative evaluation, and number of subproblem solved. So basically what they show us is percentage of problems here on the vertical axis for which a certain solver was within a percentage of the best solver. So the higher the curve, the better the method. So in this case, we see here that in terms of function evaluations, AR3 methods with different accuracies for the subproblem solved are better than AR2. Okay, and similarly for number of derivative evaluations and number of subproblem solves, especially one of the AR3 variants is better than second order. So we were very encouraged by this. We did very proper, code development. We didn't, show this on things. We didn't overtune. The test set we followed good practice. We did various improvements. I don't need to tell you about them to see how to get an efficient method. But I want to show you something very interesting that happens for third order. So now I'm getting more into how to minimize these polynomials that I have to do at every iteration. So in my algorithm, okay, so this is my local model, okay, for regularized cubic model, okay, for different values of the regularization weight. So the curves correspond to different values of the regularization weight, and I was at a certain iteration. And here is my third order model for different values of sigma, different regularization weight. So what happens here is that in theory, in many respects, you would like to have sigma large. So you put a large weight on your step, and then what happens is that, of course, your model becomes more like this, okay, here. If sigma is small, then the third order starts to have this effect on the model. If sigma is 0, because of the third order, I have third order polynomial is unbounded below. As I add sigma, the model starts to be bounded below, but its global minimizer is somewhere here, far away from the origin, which is here my base point. Okay, so I have to be careful because I may not be able to decrease my function at that point. My step may be too long. Okay, but however, if at that point I managed to decrease my function, I would have made a lot of progress. So we have this kind of tension that numerically you would like your regularization weight to be small, but then you may not decrease f, so you get a lot of steps that you reject. On the other hand, if sigma is very large, then your step will be very short and you may just take too many iterations and not see any advantage from third. You don't have this issue at all for second order. In fact, there are even more complicated problems. There is some discontinuity here because you jump from one solution to another minimizer as you adjust sigma. So there are more problems in this model minimization. And you have to be very careful for best efficient method, which minimizer of the model you choose. So this got us into thinking, okay, let's think more about how to solve these polynomials in each subproblem. Okay, so most of the rest of the talk is about how to solve this polynomial. So in this, of course, I would love to answer more on what is tractable in this, what is polynomial, I can do in polynomial time, what I can't, and so on, as well as getting an efficient method. So I want to do both. Okay, so now I want you to think that I stopped thinking about how I go along my landscape path, but that I'm at some iteration k of my algorithm, and at this iteration k, I'm going to, let's fix it that I'm talking about p equals 3. So I have a third order model. Okay, I don't care about k anymore. Okay, so I can assume that f at xk is given, right? The gradient is given, so it's fixed for all purposes here. The Hessian is fixed, and I have this third order tensor, and then sigma is fixed. Okay, so this is my problem data at the iteration. and I have to minimize this polynomial. Okay, this is symmetric matrix, this is symmetric tensor, and this is the two norm. Okay, right. So what do I know about the solution of this problem? Let's say for my algorithm, I only need local solutions. So for my complexity bounds, for my practical method, I need to know something about the local. But okay, if I could do global efficiently, sure, why not? Okay, so yeah, right. So what do we know in terms of hardness? Well, if sigma was 0, okay, this is NP hard. So if there is no sigma, this is NP. Okay. In fact, if sigma is small, almost surely this will be NP hard because this third order term here will dominate it, and there is this result of Nesterov and other people that show that minimizing a cubic polynomial over a ball is NP hard, right? So if we are close to that, context, then we will be NP hard. Okay. Assessing convexity of fourth order, okay, is also strongly NP hard, but don't worry too much about that for now. I'm not so worried about making things convex here because I mean the non-convex world in general. Okay, so I'm going to talk about two things essentially here. All right, first I'm going to talk about developing algorithms that minimize this in such a way that at every iteration of this, inner, algorithm, I have a tractable subproblem that's polynomially solvable. And then I will tell you about how could I convexify it so that I get SOS convexity into this. So these two things I will talk about. Okay. Right. So. Okay, so this is the first context. So I have this. So I have this M3. This is what I want to minimize, and I'm going to generate now iterates Si. Okay, Si that minimize this problem. So I'm at some base point at 0. I start from from S00, for example, and then I just iterate this. So I minimize iteratively this model M3. Okay, I can expand it in Taylor, of course, to fourth order because the Taylor expansion will be exact. This is a okay. So I want to get a small gradient. So I'm still looking at local minimization. That's all I need really. Getting the gradient of this model small by iterating. So now I'm going to approximate this M3. Okay. At my base point Si by some model. So what is a good model of this polynomial? A good approximation of this polynomial I'm trying to minimize. That is tractable. Okay. Well, the first idea is, okay, what is it making it not tractable? The fact that I have third order here. Yeah. Okay. So this, I'm not sure. This is obvious to you, but let me just say this again. Well, I will explain in a moment. A quadratic polynomial in n variables with a non-convex matrix here potentially, plus any two norm here to power greater than strictly greater than 2. Okay, let's make it integer so that it's a polynomial. Okay, but it doesn't have to be. This is I can solve tractably using ideas from. Okay, you can view it as S lemma, kind of, you can view it with trust region characterizations and so on. Okay, so what is bothering me is this third order term. Okay, so let me erase it, okay? But of course I have to capture it somehow, okay? This is interesting, and I want to mention this to you because I don't know if in your community this is maybe well known, if you've seen this approach with secular equations from trust region, because we can, no, maybe not, I'm not sure. So the reason we say it's tractable is that we can characterize global minimization. So assume there is no T, okay? So quadratic plus piece order norm of the step. I can characterize global minimizer of these non-convex models I can characterize them, and then I can solve them. I can solve this characterization. And this is how we can show we can get a polynomial approach. There is also, there is other reformulations. There is eigenvalue reformulation. This is essentially hidden convexity. It's the same idea you can get hidden convexity. And this approach here, I have to find lambda and S. Okay, this starts to look more like S lemma, because you have to show that you can get a linear combination that's positive semi-definite. Okay, so right, so nonconvex quadratic plus two norm regularization. This is solvable. So then the idea is, okay, take this tensor. If this tensor is not too large, try to express it as linear combinations of the second and fourth order here. So I'm going to take this and break it up by a linear combination of quadratic terms and fourth order terms. Because I don't care that it's hi there. It can be any hash. And I don't care what sigma is as long as it's positive. Right? So I'm going to change the term here and here to capture this cubic. So I'm taking this and I'm breaking it up into a part that goes quadratic, a part that goes fourth. Okay, so take the cubic and split it as this linear combination. And then I can solve this model, I can solve the resulting model. So I have a resulting model that's quadratic, potentially non-convex, plus some other weight here with okay, so so this we can solve, each one of these. And so this one is convex here. So this controls convexity, and this governs how much I regularize my model. Okay, so there is a paper of Nesterov that does this for the convex case. So again, you remember that I told you that when F is convex, there are very nice things happening to these models. You can make them convex. And the key insight of Nesterov was that, in fact, what you can do, for example, in this third order plus fourth order regularization, the third order tensor for a convex function is small. It's small, and it can be represented by second and fourth order, and so you can eliminate it from your subproblem. So what we try to do here is to extend essentially this approach to non-convex case. Okay, so anyway, so we can do that, and then whenever my underlying function at the base point is convex, I recover Nesterov's result, in which case my model minimization can be done with linear rate of convergence. And then I have other cases corresponding to the non-convex case, and so I can quantify how many iterations I need. Okay, what are other ideas? Another idea, okay, so I've eliminated third order. I've replaced it by second plus fourth. Yeah. Yeah. Yeah, so I assume that I'm in some level set of my model. So in this level set, look, so essentially I am. Yes. So I'm in a bounded image, but moreover, I iterate on this model. So I approximated that one iteration locally with respect to my entry model, then I take a step, then I approximate it again. I again replace the third order. Yeah, so it's an iterative process, yes. Okay, so now what we were trying to do was, okay, so now let me try to add a bit of third order. Can I state tractable? So then we said, okay, so replace now the third order in my M3 model, replace it with a multiple of a 2 norm to power 3. Okay, so this, and then I also can adjust my fourth order term here. So now I try to allow a little bit of third order in, but in this very structured way. This beta here can be negative, so I don't necessarily have a double regularization. I allow this beta I to be negative to capture at least some approximation of my tensor. The nice thing is that we can show that this is tractable as well. in most cases, this model can also be solved to global optimality. Using similar ideas for quadratic. Okay, so I'm just sketching some ideas. So what could be good choices of beta I here? Well, I could choose to be, some approximation of my tensor along the current direction xi. I could take the trace, for example, of my tensor, and I could put that in BI. So we can analyze this framework, and again we iterate here. Again we iterate. The way we characterize optimality is again through this kind of extensions of kind of S-lemma ideas. We, in fact, it goes back to this transregional regularization ideas. And so what we have is that we have to solve this. We again can show some kind of hidden convexity. We have to solve for lambda and S this system. So we have this linear combination of my second derivative term plus a perturbation that has to be positive semi-definite. Here's my hidden convexity. And then I have to find lambda from this now quadratic equation. When I didn't have the cubic here, this was just linear in the norm of the step, and now I have a quadratic term. But we can, this is essentially a univariate thing in lambda, and I can look at its roots. This is how we characterize the global solution. Okay, so I've gone to a constant multiple here. So I have numerical results, but I don't want to. I don't want to exist. We can get more efficiency than if you just do plain vanilla second order on the model. Okay, I'm gonna skip this. And this scalar multiple can capture, like if you have a badly scaled tensor, you can capture some dominating direction, and we can show this later. So now we have more recent work where we allow the full tensor in, or a low rank approximation of it, or a diagonal approximation of it, and we can give the best characterizations to date of the global minimizer of this model. Now, of course, this is not truly a characterization. We can give necessary and sufficient conditions. Sometimes they coincide, sometimes they don't. Okay? But we have looked more in detail at this, and so we can include more directly. So, for example, tensor, if I can do some efficient tensor decomposition here, then I could, for my original T subproblem, then I could use that in my algorithm. I can minimize my subproblem efficiently. Okay, so connections to polynomial optimization. I've already mentioned some things, but let me mention some more recent work. So let me ask the direct question here. Choosing appropriate T+1 here so that I get a proper degree polynomial and not, square root of something, okay? Is this polynomial SOX, or is this polynomial SOX convex? It's not any polynomial, okay? It has this special regularization term. And this sigma can be large, right? And I told you that if the function from which this is coming from is convex, and sigma is large enough, Nesterov showed this is convex. But is it SOS convex? Recently, Ahmadi showed that these polynomials are SOS convex for sigma k large enough. And for hk here, positive definite. Okay. So let me. So people know SOS convex. Yeah. So if it's SOS convex, it's convex. Okay. So we can then solve this tractably in polynomial time. Okay. So here's let me just spend a bit more to explain this a little bit. So here's a plot. So what I need. So I'm talking about these special polynomials. Now they can be to piece order, but add the regularization to make it proper polynomial. So I need, so from Nesterov showed that, right? So I need both that it's coming from a fully convex function and that sigma is large enough. What Ahmadi showed is that you only need locally that the second at your base point. Okay, so let me just Yeah, so basically assume K is fixed. Okay, so let me say exactly what I mean. Assume K is fixed. So I have a given polynomial, okay, and sigma is fixed. Now, if this HK is positive definite, so the given second derivative matrix, okay, so the matrix of the second derivative is positive definite, and sigma is larger than the Lipschitz constant and then some other implicit term, but that doesn't depend on accuracy or anything like that, then you can show that this is convex. Okay, so not just convex, but SOS convex, and you only need it locally. Okay, so this is very, I think, very interesting, very interesting. These are quite special polynomials, and the gap is quite fine because also Ahmadi showed that if you had a quadratic polynomial that was not convex, and you don't have the two norm here, but you have s1 to the 4 plus s2 to the 4, it's not SOS. So it's not SOS convex. So the gap is very fine. You need a few ingredients here, and you need these two norm to the right power. Okay. So and this plot shows that as sigma increases, so sigma 0, sigma, this is sigma, sorry, s equals 0 is this base point here. So as sigma increases, this is the largest sigma, the fourth order dominates, so it brings up this third order. Okay, the third order is kind of what causes us problems, yes. Exactly. If your subproblem is convex. So in the convex world, you can do this, but my subproblem is not going to be convex because I work with F non-convex. So I'm now describing what these people did. But in my case, this HK will not be positive definite because I have a non-convex F that my model is coming from. So at some iterate, I may be concave, I may sit on a saddle, who knows where I am. Okay, right. Because first of all, I thought it would be interesting to this audience to see these polynomials and what we can do with them, one. And two, because I can take my non-convex, so this is one thing we've done, I can take my non-convex model, perturb this, convexify it, so that I have now a tractable subproblem for all degrees, for all P, with appropriate regularization. So I can do that based on this work. So for example, I can compute the smallest eigenvalue of this matrix and add a perturbation here with the negative of that and convexify my model. So I was going to tell you a bit more like where this SOS convexity comes from, okay? Right, so basically what we do is we say, okay, take your local model in your ARP algorithm and convexify term, okay? Choose sigma large enough, you can do it adaptively in the algorithm. You get a globally convergent method in the non-convex case with tractable convex problems at every iteration. There is a downside, I lose the worst case bound. So this convexification of the model here, because essentially I added two norm regularization to my model. So I have a quadratic regularization plus some other higher order regularization. And that quadratic regularization destroys my complexity bound, my overall complexity. Okay, but it's doable. So we can transform these ARP methods to have tractable with this SOS convexity idea. And this quadratic regularization term is actually crucial for proving the SOS convexity. So we have a full framework that takes Ahmadi further, gets global convergence, gets a method that applies to non-convex problems, and so on. So I can tell you how Ahmadi showed this. If the function is convex, then we recover with our approach Nesterov's bound. So things are good, but in the non-convex case, we lose the optimal bound of our method. Okay, so just to say what we are thinking about now, we are thinking about how can we drop this artificial convexification of the model. So here's my theoretical question that I'm trying to solve now. I want to allow this age to, a local age to not be positive definite or positive semi-definite. I don't assume F is convex in any shape or form. Then if I choose sigma large enough, is this SOS? Not SOS convex, clearly, but is it SOS? As sigma grows, I will have just a small pocket of non-convexity around my base point, and everything else is very nice. So I'm not sure. We are working on this to try to see where is my third order causing me problems if sigma is large enough. If sigma is not large, this is definitely not SOS. This is NP hard. But if sigma is large enough, under what assumptions on the third order tensor can I show that this is actually SOS? Not SOS convex, but SOS. For tractability, I equate it with having something solvable in polynomial time. Well, if I finish at the first level with solving my SDP, then yes, okay, it's high dimensional and so on. And it's not practical, okay? I'm not claiming this is practical. This is not my practical. So I'm taking it as a, no, please. I'm taking it as a, if I show something is SOS, and I stop at the first level of the hierarchy, I solve it through a semi-definite programming. Well, it doesn't have to be zero. No, it doesn't have to be zero. No, it doesn't have to be zero. I don't know my minimal value. No, it exists, but I don't know my. So, okay, we can talk offline a little bit. No, I'm so, we are trying to see, can we make this tractable? Can we solve this in polynomial time, even though it's not going to be a practical approach? I will finish. Right. So okay. So that's something that interests us at the moment, to try to understand these models a bit more. And then I'm essentially done. Of course, in practice, you don't want to compute the third order tensor. You want to do some approximation to it. We have various approaches to try to do that. You can do, say, a low rank decomposition. You can approximate it by something sparse. We can do quasi-Newton-like methods. So we have started to work on this. Of course, tensor methods, just to finish, are not new because, in fact, a long time ago, in the 80s, a very famous optimizer, Robert Schnabel, has quite a few papers on tensor methods. He didn't compute tensors. He just did some approximations to them. But he found them to be very efficient in practice. He didn't have theory, he didn't have regularization. He just devised a practical method that, as it says here, took half the iterations as standard methods on average. So nothing is new under the sun, really. But this is very nice work on this inexact kind of tensors from the 80s. So that's it. What I want to say is that we were supported in this. In fact, we have been part of this center with City University of Hong Kong for the last 4 years or so. That is on tensors. That was all on tensors. Tensors and machine learning, also intersections with video, low rank decomposition. So that the team at the CTU is in engineering, and they work on very practical problems with tensor decompositions. And at Oxford, we have a team on this that has supported this work, and is led by Terry Lyons. Now this is coming to an end, so very glad to see more tensor centers. So thank you very much for your attention.
Yeah, thanks. Any more questions or comments?
Thank you for your response. If I understand correctly, you start to work under the condition that F is Lifeshitz, right?
Lifshitz continuity, yes, yes.
Okay, so my question is, if we drop that assumption, can we still find a way to work on these kind of problems? Or?
This is a very good question. So there are extensions of these approaches when you have, for example, Holder continuity of the derivatives, which is weaker, and you don't need to even know the Holder exponent. Okay, you don't need to know that in the algorithm. But if that kind of smoothness is present, the algorithm can to this. So this is the so-called idea of universal method. So there is that. There are some more extensions with prox operators and so on by a team in Belgium, in Antwerpen. They've also looked at adding prox operator to deal with when you have, for example, composite. So it's smooth plus composite. So extensions into non-smoothness. Yeah.
So favorite extensions are the functions defined with polynomial structures. If you look up my name, basically we have a long reduction, and it's beautiful. Essentially, you can work with non-smooth functions under some assumptions of finite so exceptional. But you need to like find a point for general time. A lot of the things carries over. We actually self-contained for convergence.
That is the reward class.
Yes.
Yes.
It's like if you construct the complete this which is trivial.
Yeah, so if I can, so to correct that, so what I was saying about Holder was kind of what you can prove about this. When it comes to practical method, what people do is often they just run this kind of smooth methods for non-smooth problems, as long as you because of course you will have just points of non-smoothness or some regions. So as long as you're not in those regions, you're fine. So you kind of just keep going. Now, this has been even for second order and first order, there are quite a few words like this. You just keep going as long as you don't see this non-smoothness. And when you meet it, try to do something a bit different. So practically you can try.
Can you adapt optimization on complex?
Yes. So essentially, yes. So the way we generalize the logic is just put the set in the subprogram. So you can say take the regularization framework and just whatever say your convex set that you have, just assume that the subproblem is over this set. So of course you have to be careful to remain feasible and so on. But essentially you can put the difficulty in the subproblem. Your function is defined over a convex set. Then you say, okay, I'm going to run this framework, but every subproblem is constrained. So I minimize polynomials over the convex. Of course, you have to change your optimality measures because you shouldn't check for small grade. You have to check for projected grade some other constraint optimality. So you change your measures and you put the difficulties on top of the problem. How do you minimize these regularized models over convex sets? Okay, we just said, okay, do it however you want, but the complexity won't change because when you have your problem over the convex domain, you don't ask for more queries about the function. So the complexity problem is constrained, and it's harder. You can make it the same as the unconstrained, but you put the difficulty. How to do that efficiently?
I was thinking of
So you can do that. So you can do, say, that. So there is more work. Rates or tier form better. It's not so easy to maintain this optimal complexity bound once you go to this kind of auxiliary functions because the parameters there and so on start to depend on your epsilon and then But if you're very careful, if you use some scaled optimality measures, people good rates, theory. There is more.
Okay, so I was suggesting the further discussion for the topic break. Thanks again.